Good morning, class. We are looking at the exam 2 review, chapter 3, differentiation rules from section 3.1 to 3.8. Here's the last part, 3.7, rates of change in the natural and social sciences, 3.8, exponential growth and decay. All right, let's go back and look at a couple of examples when it comes to differentiation. Y equals ln of 3x times x plus 4 to the power of 5. And to differentiate this, the best course of action is to use logarithmic properties to decompose this. So this is ln of 3 plus ln of x plus ln of x plus 4 to the power of 5. So we are using the product rule. And then the last one, we use the power rule, we put the 5 in front. My assumption is everybody can decompose logs easily. Now to differentiate, we differentiate piece by piece. The first one is a number. The answer is 0. ln x is 1 over x. Plus 5. Now natural log, flip this over, 1 over x plus 4. And then the derivative of x plus 4 is just 1. And that's the end of calculus. We are going to put them together by adding the two fractions. First and foremost, the LCD, the least common denominator, is x times x plus 4. So we have 1 over x plus 5 over x plus 4, and we are going to write the LCD first. 1 times x plus 4, 5 times x. And we have x plus 4 plus 5x, x and 5x, they add up to 6x. So we get 6x plus 4 over x times x plus 4. The numerator has a common factor of 2. However, it makes no difference because we don't have a factor of 2 for the bottom to simplify. Always the fraction must be simplified, and we can't do that. There is no reason to worry about that. So we just move on, and that's it. So let's. All right, now 3.7 rates of change, the difference quotient delta y over delta x. Remember, rise over run, the average rate of change of y with respect to x. And there are various formats of writing. Is also known as a difference quotient. F of x of 2 minus f of x of 1 over x of 2 minus x of 1 is called the average rate of change of y, or f of x with respect to x over the interval of x of 1 to x of 2, and can be interpreted as the slope of a secant line PQ. We recognize the following limit as being the derivative of f prime of x sub 1. Instantaneous rate of change. The limit of delta y over delta x as delta x approaches 0. So if we look at this one to be the rise, this one to be the run, delta x as x sub 2 approaches x sub 1, or delta x approaches 0. A limit of f of x sub 2, this one, minus f of x sub 1 over x sub 2 minus x sub 1 as x sub 2 approaches x sub 1. This is another format. We've seen all these formats. A limit of f of x minus f of a over x minus a as x approaches a. This is more popular, limit of f of a plus h minus f of a over h as h approaches 0. Mostly this one, when we have x, is known as the difference quotient. And of course, the derivative f prime of a is the instantaneous rate of change of y or f of x with respect to x when x equals b. And we can write it in this format. F prime of a is, these two are mostly used, the limit of f of x minus f of a over x minus a as x approaches a, or limit of f of a plus h minus f of a over h as h approaches 0. All right. Now the average rate of change, M of the blue line, PQ, the secant line, the instantaneous rate of change, M of the red line, the tangent line, also known as F prime of P. Given C of x is 62x squared plus 27,500, R of x is x cubed minus 12x squared plus 40x plus 10, find the following. So we want to find the profit function. So this is the cost function. This is the revenue function. And as you know, profit by definition is revenue minus cost. So we're going to subtract the cost from revenue. We're going to distribute, of course, and we get minus 62x squared minus 27,500. These two combine and the rest basically remain unchanged. So we get x cubed negative 12, negative 62, negative 74x squared plus 40x, 10 minus 27,500 gives us minus 27,490, in other words. These two. So basically combine like terms, it's elementary algebra. Total cost, revenue, and profit from the production and sale of 50 units. In essence, for each case, plug in 50. So C of 50. 62, 50 squared plus 27,500. Put it into a calculator. $182,500. R of 50. 50 cubed minus 12, 50 squared plus 40 times 50 plus 10. Put it into a calculator, evaluate it, and you get the answer. R of 50. The P of 50, my apologies. Just plug in. 50 cubed minus 74 times 50 squared plus 40 times 50 minus 27,490. Put it into a calculator, you have the answer. However, there's an easier way, which we already have calculated R of 50. We have already calculated cost. So R of 50 minus C of 50. So you don't have to go through that. This would be faster, but I wanted to show you both ways, of course. Obviously, we are looking at basic algebra so far. The marginal cost, revenue, and profit when 50 units are produced and sold. And reminding you, here's the cost function, revenue function, profit function. Marginal in business refers to differentiation. So when we say marginal cost, that means C prime. Marginal revenue, that means R prime. Marginal profit, that means P prime. Okay, so C prime, 62 times 2, 124x. 50 units, replace it with 50. So C prime of 50, 124 times 50, $6,200. R prime, differentiate this one. 3x squared minus 24x plus 40. 50 units, replace the x with 50. R prime of 50 is 3 times 50 squared minus 24 times 50 plus 40. And we get $6,340. P prime, 3x squared minus 148x plus 40. Plug in 50 here. 3 times 50 squared minus 148 times 50 plus 40. You put it into a calculator, gives you $140. And of course, we can say P prime of 50 is R prime of 50 minus C prime of 50. In other words, the difference between these two. So you don't have to go through that. Same thing here, the difference between these two. So R prime minus C prime. Notice is 3x squared minus 24x minus 124 is minus 148. So this can be used using the previous two step C prime and R prime, but I wanted to do it individually as well. So again, perhaps it's easier just to say P prime is R prime of x minus C prime of x. P prime of 50, therefore, is R prime of 50 minus C prime of 50. Okay. Now, what does it mean? So when 50 units have been made, C prime of 50 is the approximate cost of the next unit, 50 first unit, okay, will be $6,200. Now, it's an approximation. What is the cost of the 50 first unit actually? C of a 51 minus C of 50, which means the cost function, everybody. Plug in 51, it gives you a number. Then plug in 50, it gives you a different number. The difference is close to this number. So C of 51 minus C of 50, 62, 51 squared plus 27,500 minus, put the inside the parenthesis, 62, 50 squared plus 27,500. When you calculate this, it's $6,262. Is that the same as this number? No. But what we are saying, this is close enough and it's a lot easier to calculate than this one. So C prime of 50, okay, the concept of a marginal cost is the approximate cost of the next unit. So in this case, C prime of 50 gives us the approximate cost for the 51st unit. Okay, so C prime of 100 will give us the approximate cost for the 101st unit. R prime of 50, the approximate revenue from the sale of the 51st unit will be about this much. Now, if you want the exact revenue, it's R of 51 minus R of 50 as we did with the cost. For an approximate profit on the 51st unit of a P prime of 50 equals $140. This is an approximate value of the profit. The precise would be P of 51 minus P of 50. That's what the marginal value, marginal cost, marginal revenue, or marginal profit is used in business. The distance in meters of an object from a starting point is given by s of t equals 2t squared minus 5t plus 40, where t is the time in seconds. What is the velocity of the object from 2 to 4 seconds? This is the average velocity. And what does that mean? Total distance over total time. That's what this says. So in this case, s of 4 minus s of 2, okay, over 4 minus 2. So V average is S of T sub 2 minus S of T sub 1 over T sub 2 minus T sub 1. So S of 4 minus S of 2 over 4 minus 2. Obviously, the denominator is 2. The numerator, you plug in 4, 2 times 4 squared, minus 5 times 4 plus 40, minus S of 2 would be 2 times 2 squared, minus 5 times 2, plus 40. This is 16. So you get 32 minus 20 plus 40, which is 52. 4 times 2, 8 minus 10 plus 40, which is 38. So 52 minus 38 is 14 halves or 7. And when it comes to applications, we must always answer with proper units. If units are given, units of the numerator, distance in meters, over the units of the denominator, time in seconds, therefore meters per second. What is the instantaneous velocity and acceleration of the object? What is the velocity and acceleration of the object after 6 seconds? In general, when they give you 1 point in time, that means differentiation. So V is S prime, which is 4t minus 5. Replace the t. 4 times 6 minus 5 is 19 meters per second. As far as acceleration is concerned, by definition, acceleration is the second derivative of the position function. A of t is v prime or s double prime of t. So simply put, differentiate it again. When we differentiate it again, we get the constant 4. It is not a function of t. So it doesn't matter after 2 seconds, 3 seconds, 5 seconds, 6 seconds, it's the same thing. 4 meters per square second. Just to understand why the units are so, remember v of t is ds dt. Units of distance over units of time gives you meters per second, whereas here is dv dt. Units of the velocity meters per second, units of time is second, meters per second becomes meters per square second. So the justification as to why we have the units in that form. When does the object reach a velocity of 31? So basically set 4t minus 5 equals to 31. Move the negative 5, make it positive. They add up to 36 divided by 4 is 9 seconds. The height in inches of a sunflower X weeks after being planted can be approximated by the function f of x equals 6x minus 1/4 x squared. How tall is the sunflower 8 weeks after planting? Class, even if they don't mention, include the unit. Anytime you're dealing with the application, you must put the proper unit. So simply put, this means f of 8, everybody. So replace the x with 8. This is 48. 64. 1/4 of it is 16. 48 minus 16 is 32 inches. Proper units always. And the average rate of growth from the end of week 6 to the end of week 12, average. Okay, so rise over run, delta y over delta x, f of x up 2 minus f of x up 1 over x up 2 minus x up 1. In this case, f of 12 minus f of 6 over 12 minus 6. So the denominator is simply 6. The numerator, we are going to plug in 12 and then 6. So 6 times 12 is 72. 12 squared, 144. 1/4 of it is 36. So we have 72 minus 36. 6 times 6 is 36. This is also 36. 1/4 of it is 9. So 36 minus 9. And I hope you see we can do this. This becomes minus, this becomes positive. So these 3 cancel each other. We get 9 in the numerator. Over 6 is 3 halves, units, 3 halves, an inch per week. Units of the numerator over the units of the denominator. Find the instantaneous rate of growth 10 weeks after planting. Well, first, one point in time, that means differentiation. We are going to differentiate first. F prime of x is 6 minus the product of these two is 1/2, 1/4, and 2 is 1/2. So minus 1/2 x, that's f prime of x in general. After 10 weeks, that means replace the x with 10. So 6 minus half of 10. Half of 10 is 5. 6 minus 5 is 1. 1 inch per week. And so what? What does it mean? On week 10 or after week 10, the sunflower is growing at the rate of 1 inch per week. By the way, positive, you would say growing, negative is decreasing. Okay, so this is positive. Exponential growth and decay, a quantity Q or Q of t or y of t is said to have an exponential growth or decay model. If it increases or decreases at a rate that is proportional to the amount of the quantity present, dy dt is k times y, or y is c e to the power of kt. C is the initial value, y of 0. Sometimes they call it y sub 0. What I have here, various formats of the same thing. A equals p e to the power of rt, y equals y sub 0 e to the power of rt, y equals c e to the power of kt, q of t, q sub 0 e to the power of kt. They all mean the same thing, everybody, and I can't emphasize this enough. This is the formula. Depending on the text and the context, okay? We may use Q, we may use Y, we may use P or A. These two, by the way, are the same. This is the continuous compounding. So they all mean the same thing. Now, if we stick with one of them, for example, this one, C is the initial value. In other words, if you replace the T with 0, this becomes 1. So Y at T equals 0 becomes that. K or R, depending on the formula, whether I say K here or R here, those are rates. And they are called constant of proportionality, also known as relative growth rate. Whereas dp dt, or in this case dy dt. Dy dt is ky or dp dt is ky. That means when you take the derivative, it's called the rate of growth or growth rate. They are very similar. We don't want to mix them up. So relative growth rate refers to k or r. Rate of growth, that means differentiate. Equation 1 is sometimes called the law of natural growth if k is positive, or the law of natural decay if k is negative. It is called a differential equation because it involves an unknown function y and its derivative dy dt. So dy dt is k times y exponential growth. Dy dt is minus k times y is exponential decay. And notice y is c e to the power of kt. What if we want to differentiate it? I want to show you why it works that way. If I differentiate this, everybody, I get y prime or dy dt because t is the independent variable. The answer is itself. C remains e to the power of kt remains. So the same thing. Times k by the chain rule, right? So if I differentiate this, dy dt is c e to the power of kt, and by the chain rule times k. Notice this is identical to this one. So dy dt is k times this piece, which is y, k times y. Okay, so we proved y equals c e to the power of kt resolves. If dy dt is ky, you can see y c e to the power of kt. And so now we move to Newton's law of cooling, and I will elaborate on that shortly. Dt, this uppercase T is the temperature. The lowercase t is the time, is k times T minus T sub s. This one, everybody, is a temperature as a function of T. It's a function, capital T of T. So for short, capital T. This is known as Newton's law of cooling. That if that is the case, then T of T has the formula y sub 0 e to the power of kt plus T sub s. And y sub 0 is T sub 0 minus T sub s. We are going to actually go over that with a little bit more details in a moment. We will go over that. So this is the synopsis of the section. We will go over that later on. But for now, a population of bacteria grows from 1,000 to 4,000 in 3 hours. Assume exponential growth, find the population in 6 hours. And there are a couple of different ways of approaching it. And this is something, by the way, we have seen we've seen it in algebra. Okay, but what is it that we need to do here? Okay, given y of t, we're going to use that formula, exponential growth, c e to the power of kt. C or y of 0 or y sub 0, the initial value is 1,000. 3 hours later, that means y at 3 is equal to 4,000. Okay, so having that, this formula, everything is known except k. So we are going to find k and therefore y of a t, and then we plug in 6. That is the process. I want to explain the process to everybody. Okay. So as far as the formula is concerned, the initial value, c or y of 0 or y sub 0. Just remember, if you plug in 0, you get c, right? So that's 1,000. So the formula becomes 1,000 e to the power of kt. If y of 3 is 4,000, so if we replace the t with 3, we get 4,000. So 1,000 e to the power of k times 3 is 4,000. So we want to solve for k, which means we're going to drop the 1,000 and change this to 4, right? Divide by. Ln of e to the power of x is x. You can either go by the definition or say, I'm going to take the natural log of both sides. Either way makes no difference. If I take the natural log, the left side is ln4, the right side is 3k. K is ln4 divided by 3. And you really have to go with a lot of decimals. If they don't mention, go with 4, 5, 6 decimals to be on the safe side, or even more, okay? So now if I go back to the formula here, okay, y of t is 1,000 e to the power of kt, and I found the value of k. So I want y of 6. Let's replace it. Put it into a calculator. Bunch of decimals. You get 16,000.18 or 16,000. This is population of bacteria. We do the rounding to the nearest whole number. Now, there are a couple of different ways to approach this, and I want to explain that. But this is, I hope you realize this is algebra. We've seen this before. So note that from 1,000 to 4,000, it takes 3 hours. So 6 hours, that means 3 hours later. So in 3 hours, it got 4 times larger. So another 4 times, that means 4 times 4,000 is 6,000. That's an easy way to approach it and coming up with actually the correct and precise answer. Okay. Not always is doable, but just in case. Again, in 3 hours, it got 4 times. So every 3 hours, it gets 4 times if it's an exponential growth. And because we are talking about 6 hours, that means 3 hours later. So 4 times 4,000. Okay. Now, and that's perfect. Another way of approaching this is as follows. K is ln4 over 3. Don't change it to that. Keep it as an exact answer and put it here. So take a look at this one. 1,000 e to the power of k t. Keep the k as ln4 over 3, the exact answer, everybody. Now we have e to the power of ln4 over 3t. We are going to play with this because e to the power ln of e to the power of x is x. And by the way, e to the power of ln x is x. Right, everybody? Both are correct. And so this one is e to the power of ln4 times t over 3. Please understand, we can play with this and write it as ln4 to the power of t thirds. And what is e to the power of ln4? It's 4. So y of t is 1,000 times 4 to the power of t thirds. And just for the sake of argument, if you plug in 6 here, 6 over 3 is 2, 4 squared is 16 times 1,000, you get the same answer. This is a precise answer, okay, instead of approximation. In fact, if you continue, when you want to approximate, you really have to use even more decimals. Anyways, when will population reach 30,000? Well, you have this formula or this formula, set it equal to 30,000. So y of t equals, missing in action, question mark, is 30K, 30,000. So you put 30,000 equals one of those. It doesn't matter. It's an approximation anyways. And so obviously I can drop the 1,000 and this changes to 30. If I take the natural log of both sides, the left side is ln 30 and the right side is just the exponent 0.4621t. So t is ln of 30 divided by 0.4621, and it's 7.3603. And the units, whatever it was, units of time, hours. So more than 7 hours. It takes a little bit more than 7 hours. Exponential decay, reminding you that physicists express the rate of decay in terms of half-life. What is half-life? The time required for half of any given quantity to decay. So a sample contains 1 gram of radium. How much radium will remain after 1,000 years, knowing that its half-life is 1,620 years? So again, various form of writing them. For example, m of t is equals m sub 0 e to the power of kt. So y equals c e to the power of kt, half-life, we can calculate it to be minus ln2 over k, or k is minus ln2 over h. Y equals c to, if you have k. If you use y equals c e to the power minus kt, then half-life is ln2 over k. Depends on how you write the formula. In any event, let me go over a couple of things here. Number one, we are going to use y equals c e to the power of kt. In other words, we're going to use positive k here. In the process, when you go through that, it becomes negative, everybody. So you can always use this for exponential growth and exponential decay. You go through the process. For exponential growth, you will have it just the way it is. For the decay, you will have a negative here. In any event, so what is the initial value? 1 gram. Y of 0 or C is 1 gram. What is the half-life? 1620. And what are we looking for? To find the Y after 1,000 years. Now, what's important to know is that in order for you to calculate the half-life, you don't need to know how much you begin with, because the concept of a half-life is this. If C represents the initial value, half-life, that means this amount will be half of C. Doesn't matter, 1 gram, 10 grams, or any other, who cares? It will be half of that. So in essence, the C, you can drop it from both sides, and you get 1/2 on the left. If you take the natural log of both sides, this becomes ln1 minus ln2, and this becomes kt, and ln1 is 0, so minus ln2. So k is minus ln2 over t, or t is minus ln2 over k, and that's the formula that I had here. This is the justification as to how we arrive at k. So k is minus ln2 divided by t. Sometimes you may be interested in calculating the t, because k is given. In this case, k is missing. You're calculating the k. T is given the half-life. So replace the t with 1620. And with a bunch of decimals, we get negative 0.000427 You want to go with a lot of decimals. So this formula, C is replaced with 1, so you don't need it, and e to the power of this times t. Again, there is an initial value of 1 here, so I didn't write it. Okay, 1. So now evaluate it when t is 1,000. Replace it with 1,000 and put it into a calculator, and it gives you 0.652 grams. So 1 gram, we start with, we end up with 0.652, about 65% of it after 1,620 years. The growth in world population in millions is estimated by the formula P of t is 8200 e to the power of 0.011 t, where t is the number of years since 2025. Find the instantaneous rate of change for the year 2050, include units. This is the roughest. Okay. So that means we want to do what? Differentiate. Instantaneous rate. We want to differentiate. We want P prime of t. So to differentiate this P prime, you have the same number. Then you have the same E. And then by the chain rule times the derivative of the exponent times 0.011. Again, the derivative of e to the power of kx is e to the power of kx times. You multiply these two numbers, so you get P prime of t is 90.2. The product of these two is 90.2 e to the power of 0.011 t. Now, the year 2050, the difference is 25 years. Replace the t with 25. So P prime of 25. 90.2 e to the power of 0.011 times 25. Put it into a calculator. You get 118.7511 units. I want to make sure we understand the units. This means dp dt, change in population over change in time. Population in millions, so million people per unit of time, which is per year. So what does it mean? In the year 2050, the world population will be increasing at a rate of this much. This much is 118,751,100 people per year. So this was million, okay? I want to add a couple of things here. Remember, y equals c e to the power of kt, dy dt is ky. Rate of growth or growth rate is dp dt, k times p. Remember, what is k here, everybody? 0.011. Relative growth rate, k is 0.11. Therefore, p prime of 25 is k times p of 25. Which is 0.11, 8200 e to the power of 0.011 times 25, and you get the same answer. So this is another way of writing it, as we were discussing the concept of exponential growth and dy dt is ky, or dp dt in this case. dp dt is kp. Okay. All right. Newton's law of cooling. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding, provided that this difference is not too large. This law also applies to warming. Think about the concept. You bring a cup of coffee into a room, it starts cooling down. Okay. Or a cold beverage. Okay. You bring it to the room, it warms up. Or both of them eventually get the temperature of the room as time goes by. That's Newton's law of cooling. If we let T of t, capital T represents the temperature, be the temperature of the object at time t, and T sub s be the temperature of the surroundings, then we can formulate Newton's law of cooling as a differential equation. Remember, differential equation, anything that involves differentiation and equation. Capital dt, lowercase dt is k T minus T sub s, where T sub s is surrounding temperature K, and the surrounding temperature, and K is some constant. Let's look at the reasoning behind that. First and foremost, this is given. D capital T, D lowercase t is K times T minus T sub s. So that is what this statement says. Newton's law of cooling says that the rate of cooling of an object is proportional to temperature difference between the object and the surrounding. So that is by this statement. Now T minus T sub s, and please understand this is T of T. So this T class is T of T. And so having said that, let's call this some function y of t. We let capital T minus T sub s be some function y of t. If this is y, that means this is k times y. K times y. So dt is k times y. Again, we let this be represented by this function. Therefore, y of t is this function. Let's differentiate. So if I differentiate this, y prime equals capital T prime minus T sub s is a number, everybody. It's a constant. It's the surrounding temperature. The answer is 0. So y prime or dy dt is T prime or dt dt, right? This is different way of writing. So dy dt or dt dt is also ky. So dy dt or dt dt is ky. And so dy dt is ky, y is c e to the power of kt, or y of 0 or y sub 0. Class, please understand this is also y sub 0 e to the power of kt. Okay, that's the same thing. So we proved that it really follows that exponential growth or decay that was discussed. And so we go back and we say y is capital T minus T sub s. On the one hand, on the other hand, it's equal to that. So let's write it down. Take a look at those two. So what is capital T of T? If you move this to the other side, becomes y of t, which is y sub 0 e to the power of kt plus t sub s. And that's the formula for the Newton's law of cooling. Let's look at it at lowercase t, time equals 0. So if we replace this guy with 0, T at lowercase t equal to 0 is y sub 0 e to the power of 0 plus t sub s. Okay. As you know, e sub 0 is 1. Okay, not right. Okay. So t of 0, which is the same as t sub 0, that is the initial value, is equal to y sub 0 plus t sub s. Therefore, y sub 0 must be t sub 0 minus t sub s. And so it gives rise to the following formula. T of t is y sub 0 e to the power of kt plus t sub s, and y sub 0 is the difference in temperature, T sub 0 minus T sub s. So believe it or not, that was the proof, everybody. And we are going to look at an example. A 180-degree turkey is removed from the oven and placed in a 74-degree Fahrenheit room. After 15 minutes, it has cooled to 136 degrees Fahrenheit. Find the general solution for capital T. All right, so first, you read the question, and it's extremely important in math to write the given symbolically. So 180-degree turkey, that means that's the initial temperature. T of 0 or T sub 0 is this. 74 degrees room temperature. This is T sub S, surrounding temperature. After 15 minutes, capital T after 15 minutes is 136 degrees Fahrenheit. If we can go from here to the given, practically we are done, because the most important part is to recognize the given symbolically. So we are going to go with this formula. We have proved y sub 0 is T sub 0 minus T sub s. So the difference between the two is y sub 0. 180 minus 74 is 106. So we plug in this formula. Y sub 0 is replaced with 106. T sub s is replaced with 74. Everything is in shape, except k is missing. So T of 15 is 136. So if I replace the lowercase t with 15 minutes, same thing here, then I should be able to calculate the k. Subtract 74, you get 62. Divide by 106. On purpose, I'm not going to simplify the fraction because I want you to see where the numbers are coming from. I'm going to take a natural log of both sides. The left side obviously is 15k. And the right side divided by 15 is the k. Again, I have not simplified this fraction. I know we can do it. Anyways, put it into a calculator. You get the value of k, and you go back here and replace the k, and you're done. It's that simple, everybody. Another way of doing that is that e to the power of 15k is 62 over 106 or 31 over 53. So you can raise both sides to the power of 1 over 15 because this is 15 times k. To get e to the power of k, take a root, the 15th root, or take them to the power of 1 over 15. I hope you realize what I'm doing here. In other words, I'm doing this. This to the power of 1 over 15. This to the power of 1 over 15. That's what I'm doing. And then raise them to the power of t. So we tag along the t here as well as here. And you can write it in this format. T of t is 106, 31 over 53 to the power of t over 15 plus 74. That's another way of writing it. Again, this is precise, by the way. Either way makes no difference. So we have the formula for capital T of t now, two different formats. What is the Turkish temperature after 60 minutes? You can put the 60 here or here. Makes no difference. The numbers are extremely close. This one, 60 divided by 15, it makes it perhaps easier. Because it's 4. So you raise 31 over 53 to the power of 4 times 106 plus 74. And after 60 minutes, the temperature is 86.4065 degrees. As far as the number of decimals, you always follow the instruction. How long does it take for the turkey to cool to 110 degrees Fahrenheit? So one of those formulas, you set them equal to 110. And again, doesn't make much of a difference. And you have to solve. Obviously, we're going to move the 74 and subtract it from 110 to get 36. Divide both sides by 106. Either write the format or just take the natural log. Natural log of the left equals natural log of the right. The left becomes just the exponent, which is negative 0.0357540, and the right is ln of 36 over 106. Again, I'm not simplifying the fraction on purpose. So t is the right side divided by the coefficient of t. By the way, this number is negative because it's less than 1. And you put it into a calculator, it gives you 30.2, about 30 minutes. Again, it depends on how they want you to answer it and how many decimals. All right, put on your detective cap, CSI. A dead body was found at 1:30 a.m. when the temperature was 55 degrees Fahrenheit and the body temperature was 87 degrees Fahrenheit. We are going to assume normal body temperature is 98.6 degrees Fahrenheit. Recently, there have been a issue with that. They have updated that. But in any event, 98.6 degrees Fahrenheit, still most people believe in that. So 1 hour later, the body had cooled down to 85 degrees Fahrenheit. Of the 3 suspects, Goblin had an alibi for 10 p.m. and after. Mickey Mouse had an alibi between 7 and 10 p.m. SpongeBob had an alibi until 12 midnight a.m. Who has a good alibi? So what do we have to do? Well, at t equals 0 or 1:30 a.m., the surrounding temperature is 55 degrees and the body temperature, T as, you can say T, capital T of 0 or T sub 0 is 87, and 60 minutes later, capital T of 60 is 85. So this is the given as we look at this situation. So first, the given. What should we do? We have to calculate the temperature at what point in time must have been 98.6 degrees Fahrenheit. And that will help us find the situation as to who is guilty. So we start with the general formula, the Newton's law of cooling. Capital T of T is y sub 0 e to the power of kt plus T sub s, and y sub 0 is T sub 0 minus T sub s. So this means 87 minus 55. So capital T of T becomes 32 e to the power of kt plus T sub s, which is 55. So we have the formula almost. What is missing in action is k. We need to find the k, and we use T of 60 equals 85 to find that. That will help us find the answer. So T of 60 is 32 e to the power of k times 60 plus 55 equals 85. And we're going to subtract 55 from both sides. We get 30. Let me just actually erase the book and just do it this way. So divide both sides by 32. Again, we know this is 15 over 16, but never mind that. Take a natural log of both sides. So this becomes 60k. This is natural log of 30 over 32. Dividing by 60, we have the k, and putting it into a calculator will result in almost negative 0.001075. Remember, you carry a lot of decimals, everybody, okay? And now, capital T of T, we write the formula. 32 e to the power of negative 0.001075 t plus 55. So that's the formula for capital T of T. Capital T of what time is 98.6? So that means plug in capital T as 98.6 and find the missing lowercase t. Move the 55 and subtract it from 98.6 to get 43.6. Divide both sides by 32. Take the natural log of both sides. The left side just becomes the exponent. Find t by dividing the right side by the coefficient of t, namely negative 0.001075. Put that into a calculator. Negative 287.7, roughly negative 288 minutes, meaning the body was found at 1:30 a.m. Subtract this many minutes, so 1:30 a.m. minus 288 minutes, that makes it 8:42. And just to give you an idea, class, in case, 300 minutes means 5 hours. 1:30 minus 5 means 8:30 p.m. So Goblin had an alibi for 10 p.m. and after. That's not good. Mickey Mouse between 7 and 10 is good. SpongeBob until 12 a.m. is good. Goblin doesn't have a good alibi. That's how calculus can help solve a mystery, a murder mystery. Fascinating.